It is a tremendous pleasure to have Hiroshi visiting us just for today. We're extremely happy that we ended up having him over here at the Institute today. Thank you so much, Hiroshi. And he's going to be telling us about what sounds like it will be a fascinating talk on symmetry resolution at high energies. Take it away.
Thank you. Thank you for the kind introduction. It's a pleasure to be back to IAS. I did my first postdoc here. I met Misha Bershatsky last week, actually, and we shared an office at this small building across the lawn. So thank you for accommodating my seminar during this busy conference. So I'd like to tell you about symmetry resolution. And first, I'd like to tell you the motivation for this. Let's see if this one works. Yeah. So when conformal field theory has a global symmetry, it's interesting to understand how the Hilbert space gets decomposed into irreducible representation of the symmetry. So this is what we learn in quantum mechanics undergraduate. To solve a hydrogen atom, you decompose the Hilbert space into representation of SO3, or if you are Wolfgang Pauli, you do that with SO4. And so it turns out that there is actually a rather universal property in the way that the Hilbert space of CFT get decomposed. So I would like to tell you about that. So in particular, I focus on the high energy asymptotic behavior of Hilbert space. So we look at the density of state at high energy, and then find that there is actually a universal formula on how high energy states get distributed into each irreducible representation. And I also would like to discuss how 3-point function of conformal field theory behaves when the conformal dimension of these operators are heavy. So we are considering heavy 3-point function, and there is actually universal behavior for this 3-point function for any CFT. So this is actually based on the series of work that I have written. This is part of my pandemic project, you might say, for the last couple of years. And so I'll be happy to tell you about the summary of this development. So, so let me remind you that if you have any unitary conformal field theory in these space-time dimensions, and if you calculate the partition function, e to the minus beta h, beta is inverse temperature, h is Hamiltonian, and you take trace over Hilbert space, then in the limit of high temperature, there is a thermodynamic behavior. So the Helmholtz free energy is proportional to the volume of the Cauchy surface. So being conformal field theory, this has to be dimensionless. So therefore, it determines the temperature dependence. So this is the undergraduate physics. And then if you do the Laplace transform of this and go into macro-canonical ensemble, then you see that in conformal field theory, the density of large conformal dimensions scale like this. And so this is true for, therefore, any unitary conformal field theory. And this coefficient f depends on the theory. So for example, in the two-dimensional conformal field theory, f is related to the central charge of the Virasoro algebra. So this is a celebrated Cardy formula. But this argument works in any dimensions as far as you have a conformal field theory. So therefore, the density of state would behave like that. And just that calculating f for specific strongly coupled theory in high dimensions is more difficult than in 2 dimensions. And so the purpose of this talk is basically to define this generalized Cardy formula. So this is a case for any unitary conformal field theory. But supposing that this conformal field theory has global symmetry, symmetry group G acting on the Hilbert space non-trivially, and the G can be finite group or compact Lie group. And so then the question is that how this gets decomposed into irreducible representation of this symmetry. So I'll discuss that for both global internal symmetry and the space-time symmetry. And as I said, I would also like to discuss how a similar idea can be used to understand the property of correlation function and also entanglement entropy. So, since there will be a series of results that I would like to present, and there will be several formula. So rather than going through each formula and explain how we derive it, I'd like to first present all the results. And if you are interested in it, you can stay. And well, if you're not so interested, you can go back to the tropical world and enjoy the warm weather. So, so that's how I would like to structure my presentation. So the first 20 minutes or so, I'll just go through what we have done. And then in the remainder of my talk, I will explain the proof method of how we have arrived at this result. Okay, so the first statement is the case when global symmetry is a finite group. So this is what I would like to explain. So if you have a group, global symmetry acting on the Hilbert space, by Noether's theorem, there is a unitary operator taking value. So for any element of the finite group, there is a unitary operator that implements the symmetry. So then you can insert it in the trace. And then what I'm going to argue is that in the high temperature limit, this becomes delta function on the group. So namely that what this means is that in practice, what this means is that actually I realized that this is not shown on the Zoom, so I might as well use this one. This might be easier. So what this means is that if G is a non-trivial element of the group, this is exponentially suppressed for large temperature. And of course, when G is identity, this is an identity, so it becomes 1. So this is what I claim. And I'm going to explain why this is the case. And then you can consider now, if once you have this formula, then you can use this to decompose this trace into irreducible representations, because you can, so this is a class function. That is to say that it is invariant under conjugating G into HG, H inverse. So this is a trace, so this is invariant under this, so it's called class function. So any class function is a linear combination of a character of group, so you can decompose this into character and compare the coefficient. So this leads to this formula that the density of state in high energy in particular representation is proportional to the square of the dimension divided by the number of elements of the group. Of course, by Planck-Shiller formula, that this sums up to 1 when you sum up all the unitary representations. So this is a correct formula for the probability. So Daniel Harrow and I noticed this and wrote a paper. And then afterward, actually, we realized that in two-dimensional case, this was proven earlier by Shrudeep Par and Genji Sun. And but we gave an argument for higher dimension. So this is the first result that I would like to present. So this is for finite group. So therefore, you have finite number of elements, and you have finite number of representation. So you can ask, well, how this generalized to continuous group, where you have infinitely many elements, and you have infinitely many irreducible representations. So that means that in order to find probability, it has to be regularized in appropriate way. So I'll give an answer to that question. And so here is an answer. So we do the similar calculation for high temperature. It's a little bit more complicated. So you just that it becomes Kronecker delta, but in higher dimension, it becomes this formula. But if, in fact, you can see that if you fix the representation and if you take temperature goes to large, this becomes 1. So then you just have this summation, which is actually the delta function on the group manifold. So this is essentially the same formula as before, except that you have this kind of regularization factor. And similarly, so then once you have this formula, you can do now harmonic analysis on the group manifold. Namely, you can do Laplace transformation or Fourier transformation on the group to turn this into the, sorry, once you have this, you can do Laplace transformation on the temperature, and you can turn this into microcanonical formula, where the density of state in particular representation is proportional to the density of state for all state, but with this factor. Okay, so let me summarize this in the next page. So here is a summary of what I told you so far. So this is the formula for the decomposition of high energy state into irreducible representation of finite group. And this is for continuous Lie group, compact Lie group. And you see that these two formulas are very similar. They are both proportional to the square of dimensions, except that for continuous group, you have this additional factor. And the reason for this is essentially that so that if you sum over all representation, this can sum up to 1. And but for example, if you fix the representation and take delta to be large first, then this becomes 1. So then these two formulas are essentially the same. So the statement, therefore, is that if you pick some random state in a very high energy and ask what the probability of finding the state in particular representation are, and then take the energy to be very large, then both probabilities are proportional to the square of dimensions. So this seems to be rather general statement. So there was actually a very interesting talk that I attended by Korea recently about a distribution of random representation. He considered some kind of regular representation and considered some random tensor product of them and how this is decomposed. And he found some formula which is very similar to this formula. So there might be some connection to this type of phenomena. So this is one set of results that I would like to present. And so another thing that I would like to, so I wanted to explain why this is interesting. So one of the interesting things is the following. So this is actually, in some sense, already contains lots of interesting information. So supposing, for example, you have a conformal field theory, and suppose your conformal field theory has fermion in it. Okay, doesn't have to be supersymmetric, just some theory with fermions. So that means that this theory has a Z2 global symmetry, that is fermion number parity, that you have a symmetry to flip, to give you minus for fermionic state and +1 for bosonic state. Apply this formula. So G is 2. So that means that for high energy, you have exactly half probability that the state is fermionic and half probability that you have bosonic without supersymmetry. So even without symmetry, just knowing that you have fermion number parity, you know that high energy state, almost half of them are fermionic and half of them are bosonic. There's actually a very interesting paper by Yimin Cheng and Joaquin Treachi recently about calculating both the Bekenstein-Hawking entropy for a black hole and also the Whitney index for the same black hole. And then they found that even for non-supersymmetric, not the Whitney index, but the trace of -1 to the f. So even for non-supersymmetric series, there are actually exponential suppression for the trace of -1 to the f. So that's like a more quantitative refinement of this formula. So this formula shows that for large energy, there is approximate cancellation between fermions and boson, and Yimin and Joaquin's paper give you more precise estimate of this when CFT has holographic dual. So you can extract lots of interesting things out of this formula. Okay, so that's what I said over here. You can also apply similar formula to decompose entanglement spectrum in symmetries. So for example, suppose you have a conformal field theory. So here I'm drawing it in one plus one dimensional context, and decompose the space into some domain and its complement. And then suppose you are interested in calculating entanglement entropy or entanglement spectrum for this decomposition. So then you may consider, instead of just calculating von Neumann entropy or calculating spectra of this density matrix, you may consider first decomposing it into representation of the symmetry if the conformal field theory has symmetry. So we are taught that in order to do this calculation more carefully, you need to choose a boundary state at the end of this boundary. So I assume that there is actually a boundary state which preserves the symmetry, and so the anomaly, symmetry has no anomaly in it. And in that case, we can make statement about the decomposition, and the statement is essentially the same as what I said before. So here is a caricature. So in order to do this calculation, in order to do this entanglement entropy calculation, we're going to cut out the end point of this domain and insert some symmetry preserving boundary state and calculate the entanglement entropy. And so you can do that by projecting that in some particular representation. And then, so again, this is what we found. So if you calculate Renyi entropy, then it is actually log of square of the dimension, proportional to the log of square dimension in the limit when the size of this regularization surface is smaller compared to the size of the domain. That is a limit when we want to calculate this entanglement entropy. And this same dimension squared dependence appears for both finite group and continuous group. So this is a sort of entanglement entropy version of this calculation. And so we can also do this calculation for decomposition of the Hilbert space into representation of rotation group of the space. So supposing for that we put conformal field theory or d-dimensional conformal field theory on d-1 dimensional sphere times the time. And then on the d-1 dimensional sphere, you have SOD rotation acting on it. So we may consider decomposing the Hilbert space into representation of rotation group, so parameterized by the spin angular momentum. And then, so what we do is that this is capital L is the angular momentum generator, and omega is the angular velocity. And then we can do this decomposition. So here is some calculation of what the Casimir energy for the sphere should be. So we need to offset the amount to translate this energy spectrum of H into conformal dimension. So there is some discussion on this here. And so if you do that, so here is a formula that we derived. So the big formula. So let me explain. So this formula applies to any dimension. So this is conformal dimension. L is an angular momentum. In order for this formula to fit into one page, here I assume that I'm just turning on one component of angular momentum. We have a formula for more generic configuration of angular momentum, but for the sake of compactness of formula, and just to demonstrate that we have a formula, we can write this out. Actually, after we did this calculation, we learned that Edgar Shugarian derives the same formula by using different method. As I'm going to explain you, our method actually allows us to actually estimate also the correction to this formula systematically. And so this you can think of as a higher dimensional generalization of a more refined Cardy formula, which include which decomposes the density of state to the left moving conformal dimension and the right moving conformal dimensions. So if you substitute d equal 2 in this formula, this becomes this. You might want to equal 3.
Can I ask you a question?
Yes,
Don't
please.
you need a weight vector? Don't you need a weight vector? For you're talking about a representation of a higher dimensional rotation group. So is L, you need a weight vector, right? I mean, you need several parameters to specify representation. What is L?
L is one of the components of angular momentum. So we have a formula for when in high dimensions there are several L's, and it's actually flow of half of dimension or something like that. And but here I just wrote a formula when I just turn on one of the angular momentum components. If you look at our paper, you can see formula for general configuration of angular momentum. I just wanted to fit that into one slide. So did I answer your question? Whoever that is?
Yes, thanks.
Thank you. Okay, so one might worry that what happens when d equals 3, but when d equals 3, actually these two leading term cancels, and this becomes finite in the limit of d equals 3. So and then this gives you the correct formula. So this is another result that I would like to present. So I'm doing, this is an abstract of my talk. So I'm just presenting a series of results. And so this is a summary. So so far, so for finite group, high energy state get decomposed into representation in this way for continuous group and the rotation of spacetime, spacetime rotation, namely in terms of spin. We also have a formula for decomposition of 3-point function into representation of conformal groups. So we consider like 3-point function, and we decompose that into conformal blocks in for 3-point function. one of the technical complications in higher dimension is that even for 3-point function, there are actually several conformal blocks. So we need to actually work out the conformal blocks in higher dimension. But you can see that because first of all, rotation group is non-abelian. So there are several representations. And so I will explain later how you actually work out the conformal blocks for 3-point function in higher dimensions. And so therefore it's parameterized by the choice of conformal blocks. But anyway, so this is a formula that I will actually explain later how we derived it. And so one thing that I would like to note, so I will explain how we did it later. But one thing I would like to note is that for this generalization of Cardy formula and decomposition of 3-point function in high energy, there is actually, we only need to know one parameter. So if you have this one parameter, which in the case of asymptotic density of state comes in this coefficient of leading exponential, then it's also control the asymptotic behavior of the 3-point function. So there's a reason for this. Both comes from evaluating some partition function in the limit of high temperature. And so that's what I'd like to explain. Okay, so the reminder of the talk is a proof method, but before we go into that, let me just present the formula that we obtained, and then maybe pause a moment to see if there is any question. L dependence for D core 3. No, there is a L dependence. As I said, there is L square over here, there is L square over here. If you take D core 3, the leading term, the pole at D core 3 cancels, the subleading term has L square in it. Okay, no other question? Okay, so let me explain how we have arrived at this result. And I made use of the method of thermal effective field theory. And so this actually I learned from the paper by Shiratsu Miwara and his collaborator. I think we might have done this here, I don't remember. And also the paper by Zohar Komargovsky and the collaborators. And so here is the basic idea. So it's a low energy effective theory idea. So that means that you identify some gap in the spectrum and you try to write down, simplify the model in low energy below the gap. And the gap we are considering here is a temperature. So suppose we consider a conformal field theory in D dimension compactified on the thermal circle of circumference beta times some compact Cauchy surface. And take high temperature. So then you would expect that the generic state would acquire thermal mass, because if you calculate 2-point function, then there are thermal disturbance between them, and then the 2-point function would decay exponentially. There are some few exceptions to this rule. So for example, if you have a massless scalar theory in D dimension, if you compactify it, then in D-1 dimension, you still have massless scalar field as the low energy degrees of freedom. So, but as far as I know, that's sort of only genuine counterexample that I know of. And then most other cases, all the states get lifted by mass of order of temperature. And so I assume that is the case. And we'll see later that if you consider massless scalar theory and apply it to a formula, there are actually corrections that comes in logarithm of temperature. And we can trace that into the existence of light degrees of freedom, that this assumption does not hold. But I assume that all the states get lifted by the order of temperature, by the mass of order of temperature. And if so, the low energy effective action is written entirely in terms of background field. So you can put some background field on this geometry like metric. And also if you have global symmetry, you can twist this circle by the action of G, which is the same as considering non-trivial G bundle over this thermal circle. And so if you do that, the low energy effective theory, you want to write it in a diffeomorphic invariant way. So the leading term for high temperature should be cosmological constant. But cosmological constant can depend on the holonomy of the group around the thermal circle. And then here I have written dot, 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 and these are terms suppressed by 1 over t square. So for example, if you have, you can turn on background gauge field with respect to the group G, then there can be field strength square, which can be suppressed by 1 over t temperature, or this holonomy may be position dependent, in which case you can have a kinetic term. But those are suppressed by 1 over t squares. And so this is a leading term. So I focus on this one. And the good thing about this, one of the wonderful thing about this low energy thermal effective field theory approach is that this is very general. That is that once you write this low energy effective action in the diffeomorphic invariant way, in terms of background field, then we can put it on any Cauchy surface. So we can put it any Cauchy surface we write, and then we can calculate this V of G. As I'm going to explain, this V of G is what we need in order to obtain the result we find. So we can choose this Cauchy surface in a way that is convenient for us. So what I'm going to do is choose this Cauchy surface to contain additional circle. So then the total space has a thermal circle and this additional circle on the Cauchy surface times the rest. And then we can play a trick similar to doing modular transformation in two-dimensional CFT, namely exchanging these two circles. And so of course, unlike the case of two dimension, we cannot fully use this. For example, in two-dimensional case, that is very useful because then you can relate ultraviolet quantity like the coefficient F we want to calculate to infrared quantities such as conformal anomaly. We don't have power to do that, but at least what we can show by using this kind of argument is that this function V of G is related to the lowest conformal weight of the G twisted sector. So let me explain what this is, how do we do that. So yes, please.
It's a direct product.
So later you'll see an example where it is not a direct product, but here it's useful. Well, I'm trying to consider the simplest case where it is direct product. If it is not direct product, basically you are turning on some background metric. But why do you ask?
It's not if S1 tilde and sigma d minus 2 is it's not a direct product. Then when you exchange it, then you don't get back the same geometry.
Yeah, but as I said, I can choose any geometry I like. So I'm not obliged to take that geometry.
One theory to another.
Yeah. So I'm choosing the simplest one that does the job for me. Because this is diffeomorphic invariant low energy effective action. So whatever geometry I choose, smooth geometry I choose, you get the same answer. So here is an argument. So suppose the total geometry, space-time geometry, is this thermal circle times another circle, which I call S1 tilde, times some compact direction. And then suppose I evaluate this low energy effective action on this geometry, then I say that there are two interpretations of this calculation. One is the original interpretation, which is that you have a thermal circle here, and I'm evaluating this Poisson function. But alternatively, you can think of this thermal circle as a part of your Cauchy surface and think of this as your thermal circle. But now what you have is that you have this domain wall implementing the symmetry group action G or at a point on this Cauchy surface. So namely that this is now this circle direction is in the twisted sector, twisted with respect to G. And then taking this circle to be small by going to high temperature, beta goes to 0, is the same as going to the low temperature with a very long thermal circle. And so then you just basically evaluate the ground state energy. And if you work out the scaling of all these space, then you can actually see that this V of G is nothing but the lowest conformal weight of the G twisted sector. Okay, so here is one assumption we make, and currently actually Shuldeep Pal and Jenjin Sun and my collaborator in San Diego is working to give more precise derivation of these statements. But here I take it as an assumption that if G is a non-trivial element of the group, then if you consider G twisted sector, and then the ground state energy is actually greater than that of the true ground state, the untwisted ground state. That seems to be a reasonable assumption. Yes, you have a question.
Casimir energy in more than 2 dimensions.
Well, this is that. Well, so there is a state operator correspondence in any dimensions. So you can. So one way to define V of G is a conformal dimension of the corresponding to the ground state of G twisted sector. You can think of this as also Casimir energy on the S1 times some compact space. It's a ground state energy of the G twisted sector.
That doesn't depend on counter terms in any way.
It doesn't depend on.
2 dimensions is an anomaly, so it doesn't depend on counter terms. And higher
It doesn't depend on what?
Counter terms of any theory that you study.
No. Okay. Well, it's a well-defined physically observable quantity. It's a conformal dimension of the ground state of the G twisted sector. So if this assumption is true, then what it means is that if G is a non-trivial element, then V of G is greater than 0. If G is 1, then it takes the lowest value. So therefore, this is so for large temperature, for G non-trivial, it's exponentially suppressed. So that's the statement. So therefore, we obtain this formula. So for finite group, this is what we teach for undergraduate group theoretical method in physics. So then you can just substitute that into here, and then you can decompose this into irreducible representation, and then we obtain this formula. So basically, this comes from this one. The square comes because each representation, of course, has dimension r. So therefore, you have dimension r squared. It's a little bit non-trivial, counterintuitive that it comes in dimension square rather than dimension. But basically, one dimension factor comes from here, and the other dimension factor comes from here.
So, Hirosi, I have a question.
Yes, please.
I'm not sure I
Who is
understand.
that, by the way?
Sorry?
Oh, it's Greg. Oh, okay.
Yes, that's Greg. Yes. So I'm not sure I know what the twisted sector means in higher dimensions. I mean, it's the lowest conformal weight. Doesn't it depend on what sigma d minus 2 is?
No, well, so it's twisted in the sense that if you go around this S1,
no, I understand that. I understand that.
And it's a trivial bundle over here.
Yeah, I got that. But you know, you're looking. Doesn't the Hilbert space and the Hamiltonian actually depend on, you know, what spatial manifold you have? So your spatial manifold is S1 times sigma d minus 2. But surely the Hilbert space depends on what the sigma d minus 2 is.
Yeah, but I claim that the conformal dimension V of G is independent of it.
Okay. That seems like a non-trivial claim to me.
Edward has a comment on this.
Okay.
To start with infinite volume, where this would be clear because G labels the vacuum state of the theory on S1 times RD minus 1.
Oh, okay.
If you have the infinite volume limit, it becomes clear that you can make a statement for any large finite volume.
Thank you. Yeah, effectively, we are sort of going to infinite volume because the volume of this space is going to infinite in the limit of high temperature.
The question is clarified by the fact that what you're saying is completely sharp in the infinite volume limit.
Oh, okay. Thank you. Yes, I should have said that. Okay, so this was a formula for when the group is finite group, and so we can ask what happens to compact Lie group. So we are suppose we are interested in understanding this behavior of this function V of G in the neighborhood of origin. So then we may consider parameterizing it as it is a I phi exponential, where phi is an element of Lie algebra, and then we can consider expanding it. Since this has a global minimum at G equal 1, then we should be able to expand it in this way. And then, therefore, if you have this, then we should be able to write it in this way. Okay, so the same argument that I was trying to give with Shurdeep Paul and collaborator over here leads to the claim that this coefficient B is actually positive number. And so then it follows that you have this statement where this inner product is, of course, Kashmir killing form. Okay, and so now what we need to do is to do the harmonic analysis on the group manifold and write this in terms of representations. So here you have a class function, and you want to write it in terms of the representation. There is actually a nice trick of doing that, and if you know that, you don't have to do any calculation. So I was very happy we came up with this. So the idea is the following: that this actually is the solution to the heat equation on the group manifold, with the appropriate identification of temperature with the time, Euclidean time. So this solves the heat equation. And it also solves the condition that in the limit of high temperature, it becomes delta function on the group manifold. So namely that you have a solution to the heat equation with the initial condition that it's a delta function in the group manifold at the origin. And then this is that, okay? So now you can ask, you can look at it, and you can see that each term in this sum over representation is also a solution to the heat equation. Because if you take derivative with respect to temperature, you get second Casimir down. The second Casimir for given representation, if you consider Laplace operator acting on the character, then it gives the second Casimir. So therefore, this is actually a solution to the heat equation on the group. So both are solutions to the heat equation. So you just need to check they satisfy the same boundary condition. But this does, because if you take the representation finite and take the limit of high temperature, then this is just a dimension R times the character, and it's the same formula. So actually, it's the same formula as this one. So namely that in the limit of infinite temperature, this becomes delta function. So that way you can see that actually the harmonic analysis of this on the group manifold gives you this. Okay, so that's a sort of quick and dirty argument that this works. Okay, so then once you have that, you can do the Laplace transformation with respect to temperature, and the density as a fraction of state in high energy going into particular representation is again square of the dimensional representation, except that you need to have this regularization factor because there are infinitely many representations. Okay, so that's sort of a derivation of this formula. So any questions so far? Is that clear? So I made a couple of assumptions, but I hope I laid out the assumptions, and I think that we are trying to work out a way to derive it. But,
when you said you had a solution of the heat equation, you meant in the high temperature limit, right? I mean, the actual solution of the heat equation is more complicated. You know, for a circle, it would be like a theta function.
Right. Yeah. So it's a leading behavior for high temperature or short time scale. Yes.
Does it apply to, let's say, a sphere, a higher dimensional sphere?
The case when you have S1 times the sphere. Yeah, well, but here this formula is true for S1 times any compact geometry. What do you mean by sphere?
You have the spatial manifold is just S3.
Yeah. So it works. So this is an important point of thermal effective field theory. So once you write this, then it works for any Cauchy surface. And I just chose particular Cauchy surface for the convenience of calculation. But since this is written in a diffeomorphic invariant way, once you have the answer, you can apply it to any geometry, and in particular for the sphere.
I just want to understand. So the emphasis, the assumption here is like when you have a different temperature, it doesn't matter what metric you choose. So you basically can do that, right?
Right. Yeah. So but that's sort of a consequence of the sort of principle of low energy effective action, I think. Another way of thinking that in high temperature you have thermal mass, so you only have short-term correlation, short length correlations. So there are no ways for the low energy effective action to see the global geometry. You only know the metric and things like that, and that's how you obtain this. Okay, so a few I think I have some time to explain a few examples. So we checked that this formula for various examples. So for example, free spinors and free scalars. I told you that for massless scalar, this assumption does not work. But in fact, for sufficiently high dimension, it does work. In 2 or 3 dimensions, actually, this is actually not correct. And then there are logarithmic correction in temperatures. And but we identify that as a consequence of the fact that in low energy, you have massless scalar particles. But for wire fermions, if you have twisted boundary condition for fermions, then this is fine. The holographic example was interesting, and so that was an interesting exercise for us. So in that case, in order to calculate this quantity, what you need to do is to consider Einstein gravity coupled to Maxwell field of gauge group G, and in general, some non-abelian gauge group. And then we want to find a Bekenstein-Hawking entropy formula for non-abelian black hole. So we went through some general relativity literature and then try to find if they have actually calculated the Bekenstein-Hawking entropy for non-abelian black hole. And there are some beautiful review articles on the subject. But it turns out that there is actually some kind of long-standing puzzle in the GR community, which is that it turns out that there are actually 2 types of black hole solution with the same non-abelian charge. So one is the following. So you see that this is a class function. So that means that you can conjugate the group element G to go to the direction of maximum torus. And then you pretend that actually gauge group is not non-abelian G, but it's actually U1 to the raised to the power of the rank of the group. And then you can use actually bunch of abelian gauge field and build the standard rational Northstone black hole for this U1 to the rank group. And so that's one solution. And you can calculate the Bekenstein-Hawking entropy for this. And then there is another solution, which is sort of genuinely non-abelian in a sense that in this, so they already calculated it numerically, but the gauge field configurations are non-commutative. So these 2 solutions are in fact different. And so there was actually a long-standing puzzle about which one is more stable. So fortunately, we were able to actually identify which ones are more stable. And so the argument was very simple. So when we are interested in high temperature limit. So in the high temperature limit, the ADS black hole grows and the horizon approaches to the boundary. And near the boundary, of course, because of the gravitational effect, the amplitude of the field gets suppressed. So therefore, the distinction between non-abelian solution and the abelian solution disappears in the limit of high temperature limit. And indeed, we are able to check that the Bekenstein-Hawking entropy actually become identical for these 2 solutions. But then we actually calculated correction to that for finite temperature, and so that genuinely non-abelian solution is more stable. So at least for sufficiently high temperature, we can address this question in GR community. And with that solution, we actually were able to calculate this F and B. Oh yeah, I forgot to say interesting thing, one thing, which is that, so nobody asked about what is this B. So this B is related to this B. And so in addition to F, B is also some number that depends on the theory. So for example, in the 2-dimensional conformal field theory, if you have continuous global symmetry G, it's always upgraded to Kac-Moody algebra. And then B is related to the level of the Kac-Moody algebra. Okay, so you can calculate these quantities. We can also do this same exercise for the entanglement entropy. And in view of time, and maybe I don't go through detail, but as you can see, if you are interested in the limit when regularization size becomes small compared to the size of the domain, then basically you are considering high temperature limit. So that's why you essentially get the same formula for here. Sorry, yeah, so here I'm calculating Renyi entropy. So it turns out that this behavior is independent of n. So this is, the rho of n is like calculating fundamental entropy for rho to the n. So I had the formula. I think I had the formula. Q is the exponential of ratio of the size of the so it's exponential of the ratio of this versus this. Yeah, and so here's the definition of Sn. So it's a Renyi entropy.
excuse me, Hiroshi, now you're talking about Random entropy in states that transform in a given representation?
Yeah, so here what I'm doing is basically inserting projection operator into particular representation in the group. Assuming there is no anomaly in the group, and then there is a symmetry preserving boundary state that we can put on the edge of the entanglement domain. So, so I would also like to explain how we obtain this formula for the composition of state into a representation of spins. So the way that we did it is, so instead of inserting operator which generate action of the internal symmetry group, what we can do is twist the torus, which is to say that supposing we have a geometry which is a thermal circle times the d-1 dimensional sphere. And so I just parameterize this d-1 dimensional sphere in this way. I think there is a typo over here. Here, I meant to say that this is actually, so I don't know what happens. This is the angular direction. Somehow this disappeared. So I'm sorry for this. But anyway, so what I did was that we can actually calculate this thermal position function with angular velocity omega by twisting the thermal circle, by twisting the sphere. As you go around the thermal circle, you can twist the sphere by the amount of angular velocity. So theta A is the angular coordinate, which is supposed to be over here, so that somehow there was some problem with the PDF file, and then it's shifted by this. And this is actually what Nekrasov used as an omega background to calculate the Seiberg-Witten prepotential. And so then you can actually rewrite this in the Caltech-Klein way, that you have low dimensional metric, Dilaton, and gauge field. And a fun fact about this geometry is that actually the fun fact is this Dilaton and gauge field and the matrix now become position dependent, even though the geometry is sort of it does not have obvious sort of position dependence. But in this parameterization, there are position dependence. So you have to substitute that into the action and evaluate it. But we can do that. And then, so then if you do that, basically what this comes from, for example, the cosmological term. And if you do the integral of this position dependent things, then you obtain this formula. So one of the interesting things is that this has a pole when the angular velocity is pure imaginary I. And so this actually controls some asymptotic behavior of this thermal position function for large conformal dimension and large angular momentum in this type of limit. And so as I said, so this kind of idea of using thermal effective action to evaluate this thing originate from Bhattacharya, Lahiri, Logai, Nayagam, and Shiras Minwara, and Edgar Shugarian use similar idea to evaluate this. And we use the method of thermal effective action and obtain this formula. So I already explained this formula. So I'm just showing that this is a result of evaluating. Basically, you start with this and then you do Laplace transform with respect to temperature and angular momentum, and then you obtain this formula. So you start with this omega background, you evaluate a cosmological constant, and then you do Laplace transform. And this is how we obtain this formula. And again, we can check this in holographic case and free field case. Holographic case, we consider Kerr black hole in ADS, and then we obtain exactly the same formula. And we can also calculate subleading term in this calculation. Okay, so this is a summary of what we obtained so far. In the remaining 5 minutes or so, I'd like to explain how we can use a similar idea to calculate the asymptotic behavior of 3-point function for heavy operators. So in 2-dimensional conformal field theory, this was already done by Cardy, Maloney, and Maxfield, and also in combination of them with Scott Collier and Tsares. And the idea is that to start with genus 2 Riemann surface and put conformal field theory on it. And then you can think of genus 2 amplitude as product of two 3-point function with cylinders. And then you can parameterize this cylinder by the length of cylinder and the twist. So this is known as Whittaker-Schottky parameterization of Riemann surface. And then they consider the limit when beta is small. So then you have a heavy operator going through it. And then in 2 dimensions, you know the conformal blocks, etc. So you can actually calculate this. And this is what they did. So what I did with Nathan Benjamin, Jai Hari, and David Simmons-Duffin recently is generalize this for higher dimensions. So basically, we straightforwardly generalize it to higher dimension. So we consider 2 d-dimensional sphere and removed 3D disks from each one of them and connected by cylinder. Okay, so this is the geometry. You have the boundary of disk, you have a boundary of disk connected by cylinder, and you have 3 of them. And each cylinder has different lengths. And we are interested in evaluating this, the limit of this partition function. And then we put the conformal field theory on this geometry and consider the limit when these betas, the length of the cylinder, become shorter and shorter. And then you see that in this limit, there are actually 3 points on this geometry where the period of the circle becomes short. And we call them as hotspot. And we assumed that the leading contribution to the high temperature behavior of this partition function come from these hotspots. So I have a couple of comments about that. So initially, we were hoping that this geometry is actually a circular vibration. And then the contribution localizes to the hotspot. It's not quite a thermal vibration. But if you look at the geometry in the neighborhood of these points, then this is actually a thermal circular vibration. So we can actually evaluate the low energy effective action in this neighborhood. And we actually just assume that this is a leading behavior, leading contribution to the high temperature behavior of the partition function. This is an assumption, and it would be nice to actually understand it more rigorously. But in all other places, the geometry is smooth. And on the other hand, we can see that contribution for high temperature from hotspot is singular in temperature. So it seems to be reasonable that leading singular behavior of the partition function come from contribution from the hotspot. Yes.
Presumably, as you go away from the hotspot, the temperature becomes smaller. Right?
That's correct.
Is the gradient of the temperature?
It was important to evaluate this. Yes.
Is the gradient of the temperature small compared to the diffraction? I mean, gradient of temperature divided by the temperature is small compared to the temperature.
Okay, that's an important question. So, namely, whether you can, yeah, I don't remember off the top of my head. I think we did check that, but I cannot answer this question. Yes. Yeah. So we were careful about estimating how the circular vibration behaves in the neighborhood of hotspot. But yes, your question is quite right. Yeah, valid. I think we checked it, but I need to go back to my notes to make sure that. So I cannot answer you off the top of my head. So anyway, so this is the leading behavior that we. So the leading behavior is relatively simple. So namely that from each hotspot there is an effective temperature, effective inverse temperature for this, which goes to 0 in the limit of high temperature. And so that's what I call beta 1, 2. So beta 1, 2, for example, is a hotspot between the cylinder 1 and cylinder 2. So there is this hotspot. And then you can evaluate the period of this thermal, the local temperature, inverse of the local temperature. And there is the local angular velocity. And you can evaluate these beta 1, 2 and omega explicitly as a function of this original parameters. And so then we obtain this, and we get the same f because we are calculating just the behavior of we are just evaluating this on the low energy effective action, so we get the same f. Okay, so that's one part of the calculation. So this is a partition function. But now we have to decompose that into conformal blocks. And so this was a fun part of our project, that we need to work out the genus, higher dimensional genus 2 conformal blocks. And so I learned quite a bit about how to do this calculation. So I wanted to tell you a little bit. So both conformal, so there is this thing called conformal blocks, and there is this thing called the conformal partial waves. And both are solution to the conformal Casimir equations, but these are different bases. And the conformal partial waves are easier to calculate because there is some kind of explicit formula where you choose 3 elements of the conformal group and then just evaluate it in terms of correct Gordon coefficient of this conformal group. And we parameterize principal series representation in this way. But then, so this is actually parameterization of conformal partial waves, and we want to expand this partition function in conformal blocks. And so that requires some work, but fortunately, Caltech, Pravchuk, and Simons-Duffin had this technique called monodromy projection, which tells you that if you have conformal partial wave, you can actually extract conformal blocks. So in generally, for each channel, in this case, you have 3 channels here, the G1, G2, G3. There are actually 2 conformal partial waves has 2 sort of solutions, and corresponding to some conformal weight and its shadow. And so in general, therefore, you have 2 choices. So you have 2 to the 3 dimensional space of solution to the conformal Casimir equation. So we just need to, so both of them, both conformal partial waves and conformal blocks are solution to conformal Casimir equations. And then we just need to choose the appropriate basis for this. And once we have that, we need to choose a measure of the conformal blocks so that they are also normal and calculate the overlap. And you can do that by saddle point approximation in appropriate limit. And then from that, we can extract the 3-point function. So this is how we arrived at this result. And I pointed out earlier that this depends only on the parameter f. And the reason for this is that it just comes from the low energy thermal effective theory calculation, both the generalization of Cardy formula and the asymmetric behavior of 3-point function controlled by thermal effective action. So that's why we have the same parameter f controlling both. So once we have f, we can calculate this. One interesting thing which we do not have complete explanation is that if you look at this formula, then leading dependence for the large conformal dimension is this exponential term. And this seems to be independent of dimensions. And so we don't quite understand why there is this kind of universality. So subleading terms, like for example, there is exponential of delta to the 1/3 or delta to the 1/2. So these depend on dimensions, but this seems to be independent of space. Yes.
Depends upon the particular geometry you used.
I believe that, well, what do you mean by that? We, of course, use this particular geometry to extract this number, but it was my assumption that we are calculating this coefficient here.
At least in even dimensions, there's a conformal anomaly that affects what you mean by C. 1, 2, 3.
Oh, sorry. What do you mean by? Sorry, well, by C, you mean? Oh, so you said there's an ambiguity in the definition of C. Okay, I need to think about that. You said that ambiguity comes from conformal anomaly?
What kind of local parameters you use when you insert your 3 operators on the sphere.
In 3 dimensions?
Which perhaps you've used.
Okay. Thank you. Yeah, this is something I need to think. So I would like to end with a few questions. So this formula that we derived is valid for large conformal dimension and angular momentum, but in the limit when the difference of delta and angular momentum goes like square root of f times delta. And there is another approach called light-cone bootstrap to go to high conformal dimensions, but that is in the limit when this is actually, the difference is much smaller than the square root of delta. So it would be nice to actually interpolate between them. We are hoping that we can push our method to go to the light-cone bootstrap region, but we couldn't quite do it. So there is also an effective action parameter. The effective action parameterizes our ignorance. So it would be nice to actually be able to calculate this. And so 3D ON model such as calculated F. Ifan Wang recently told me that he can calculate also B for this model. So I'd like to understand this. And but you can ask, well, how can we calculate higher coefficient, or can you bound in general the coefficient of higher moment? And so those are interesting. In 2 dimensions, there is this amazing fact that these heavy 3-point function and the related ones are given by DOZZ formula for the Liouville theory. And why is this? I do not completely understand, although there is a relation between the Liouville calculation and 3D gravity calculation. So maybe that's the origin of this. And you can ask, well, whether there is a generalization of this. So this can be interpreted in a similar way. And another interesting thing is that the paper by Cardy, Maroni, Maxwell, and Scott Collier and the collaborator calculated this 3-point function. I told you that they actually did this calculation for using genus 2, but they did a decomposition of this in terms of Virasoro conformal blocks. But our formula is for the global conformal blocks. And so if we compare our result with their result, the answer is different. And the 3-point function in 2 dimensions in conformal global blocks that we calculated is this behavior, which is what I wrote over here. This is square root, yeah, it's like this. And for Virasoro block, this is this. And the global blocks is much bigger than, the 3-point function is much bigger than that for Virasoro blocks. And so what it means is that the ground state of the global block contains a lot of boundary gravitons. And it seems like if you have boundary graviton, you have bigger 3-point function. And so why is that? Well, could it be that also in higher dimension, if you calculate the amplitude of merger of 2 black holes into the 3rd black hole, it gets enhanced if you include the effect of gravitons around it? I'm not sure. But so it would be interesting to understand where this comes from. There is actually a couple of interesting papers by Diego Vieira, Rob Meyer, and collaborators, where they are doing this kind of 3-point function calculation in a bulk Einstein gravity. And it may be interesting to understand the origin of this from that context. But anyway, so that's all I wanted to say. So we obtain all these results by using the telescope of this effective field theory. So effective field theory is like a telescope that you're bound on the Earth, but you can see a very long distance, and in particular, the behavior in high temperature and their decomposition. So thank you for your attention. Oh, yes.
Does it make sense to also try to include d equal 1, like SYK type near CFT?
Yeah, so unfortunately, I think this calculation assumes that low thermal effective field theory approach, and I think that assumes that there is a non-trivial spatial direction. I'm not sure whether the argument, for example, the fundamental argument is this G twisted sector has a non-trivial ground state. And so this argument does not immediately apply to d equal 1, because in that case, this direction is 0-dimensional. So it could be that formula is still true, but not for the reason that I described here. I think I have not looked into this carefully, but on the other hand, I told you that this type of behavior, that square of dimension of representation, also appears in this random tensor product decomposition work by Korea-Reshetigin. And so that seems to suggest that maybe in one dimension it also works, because in one dimension it's natural that if you have some kind of you can consider you can construct high energy state by just multiplying states. So, but I don't know. It's an interesting question. But if I do know that, does it have application?
Well, there are these complex SYK, right?
Oh, okay, I see.
Some other type of.
Oh, I see. So we can compare. Yes. Yeah. Okay. Good. So there is some specific problem. Yes. Fun.
I have a minor comment on this coefficient B. So in the case of rotation, you can think of it as the angular momentum of the black hole.
B.
Well, I'm not sure if it is B. It might be a combination of B with
this
something else.
one.
Maybe it's B with something else. Parameter, which is the angular momentum, the momentum of inertia, sorry, of the black hole. Sorry, I misspoke. The momentum of inertia of black hole.
Momentum of.
I think it's called moment of inertia. Sorry,
Moment of inertia. Moment of inertia. Yes. Yeah. It's something like that. I agree. Yeah. Right. Yeah. So you mean that this type of coefficient? Yes. Yeah. I think. Thank you. Yes. Moment. Yes.
I have a question related to your last comment. So maybe I'm confused. So I think in your computation you said you're using the global block way to do the computation, and it seems that you use Sage coefficient and transfer that to a Virasoro block, or you didn't do that?
So we calculated the 3-point function in global blocks, and Alex Maroni and collaborator calculated it in Virasoro blocks, and we just compared them.
I see, but is a Sage coefficient?
It's just a representation theoretical fact, namely that how Virasoro blocks get decomposed into global blocks. You can say that, yes?
Yeah.
Yes, you can say it that way, yes.
But do we know exact formula? How do we transfer? Like...
Yeah, we have formula for this. So what this is saying is that the decomposition coefficient is bigger than the 3-point function in the Virasoro blocks. I think that's what this is. Yeah.
Hiroshi.
I had a question.
Yes, please.
So if I look at your results for the density of states, it seems to me that what you're saying is that at high energy, the Hilbert space sort of factorizes as L2 of G times a representation times a Hilbert space on which Gx trivially. At least, in the first one, I think you said this in passing, the dim R squared over G is the natural measure on the dual group that you'd get from the Peter-Weyl theorem. And I guess that's also true of the compact group. That it's also the partition function of 2D Yang-Mills on a sphere. Right?
Yeah, we are amused by this relation. I have not.
Is there some conceptual reason for that?
We were aware of similarity, and we spent some time trying to come up with an explanation for this. It would be great if we understand it from that perspective.
And so then I also had a question about when you introduced.
So for example, that would also explain this second Casimir piece, for example.
Yeah, right. I guess that's the natural measure you would get on L2 of G. On the dual group for a compact group. So, and then I also had a question about your formulas where you introduced angular fugacities for the angular momentum on the sphere. That you call them angular velocities. Oh, not that one. When you introduce yeah, that one. Yeah, and some of the formulas you had formulas that looked like a product of 1 plus omega a squared, product over a.
So which formula you are referring to? The first one?
Well, some of the formula, I didn't want to stop you, but you had formulas for for this rho sub d of L, I guess. You had some formulas where you had this trace was written with a product of 1 plus omega a squared, a product over a.
Well, let's see which one you're referring to. I'm trying to figure out. Are you referring to this one?
Yeah, there it is. There it is.
Okay.
Yeah, that formula puzzled me. I mean, don't we expect this thing to be periodic in the omegas? L has a discrete spectrum. Discrete.
You're asking how you reproduce the periodicity. I think we are evaluating it in the neighborhood of omega. So let's see. So you're asking this should be periodic in omega.
Well, the left-hand side is periodic in omega. Omega is basically
I think we are focused on the behavior near the a pole of this function. So I think there is also secret omega dependence, and this one is sort of regular at omega equal I. So I'm just extracting this piece which has singularity at omega equal
okay. Okay. Thank you.
Right, beta omega. Yes. That's right. So if you look at the leading behavior, you don't see the period. The period becomes infinite in some sense. Oh yeah, so that's another way to say it. Yeah, thank you. Yeah, that's quite right. Yes, yeah, thank you. Juan, you had another comment on Greg's earlier point.
No, that's it.
Which was in relation to 2D and Mills.
Yeah, I was puzzled about 3 things, and I asked about 3 things. So.
So you had a comment about 2D and Mills, if I remember.
Well, I know it was more of a comment question. It was that
Greg, I'm asking Juan.
I was asking why 2-dimensional Yang-Mills came up, and if there was some quick conceptual derivation of your result by somehow getting an effective description in terms of 2D Yang-Mills.
Right. Yeah. So I got it, and then Juan had some comment on this.
I think it's related.
The comment was that I thought I could interpret your results as equipartition on the dual group.
Yeah, I think that's understandable. I just wanted to hear what Juan would say.
Greg mentioned that you had this L2 of G. This I think also appears in Edward's paper on the cross product. And I think it's probably a feature of the thermofield double that you can introduce this G, some kind of chemical potential for the left and right sides. I don't know, it's another context, but
okay. Thank you.
Questions? All right, if not, let's thank him again. And I'll also remind people at the workshop as well as guests that there's still for another 15 minutes tea over in Folds Hall. So anyone who doesn't know where it is, just follow people heading to Folds Hall. Let's thank Hiroshi again for a wonderful talk. Thank you.